No? No, I didn't send you. Okay, just check.
On va commencer dans 1 minute, 2 minutes. Ça marche.
Ça rajoute un peu de société technique à cette histoire.
Bah ouais. C'est toujours au moment où tu démarres que tu te rends compte que ça marche.
Ben ici, ça marche pas, c'est là.
Donc on démarre. Ouais, effectivement. Ouais. Mais le problème, c'est qu'on les voit pas. On les entend par contre ou pas?
Vous allez. Tu peux les demander de.
Okay, this is just to check that Armando is connected and Angela Vela. Can you hear me?
Yes. Yes.
And this is Isabel. I hear you very well, and I see the slides.
This is Armando. Everything is fine here. Can you hear me? Can you hear me? No?
Oh, sorry, yes.
Armando, I hear you, but it seems that they don't hear us. I don't know.
Oh, it's okay. No, it's okay.
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 So is Angela also here? I heard only 2 people, I think. Angela, it's okay?
Yes, it's okay for me. Can
Excellent.
you hear me?
Yes, perfect.
Good.
Okay, so we are all set then.
Okay, I think you're not hearing, right?
Yeah.
You can still hear us. You can still hear us. Hein?
Comme je vais vous présenter, pas que je vais.
Ah oui.
Okay. So good afternoon, everybody. We are going to start the PhD defense of Saptarshi. Thank you for being here. So this is going to be the defense of Saptarshi Kotal. So let me introduce briefly the jury. We are only 4 to be actually here presently, and we have 3, there you go, much better. We have 3 people remotely. So we have Armando Rastelli, who is 3rd from the top, who is at Johannes Kepler University in Linz, Austria. We have Isabelle Robert-Philippe, who is senior researcher at Laboratoire Charles Coulomb in Montpellier. We have Christophe Couteau, who is here from Université Technologique de Troyes, who will be, the first 2 were the referees, and he's an examiner. We also have Professor Angela Vela, who is from Rouen University, from Groupe de Physique des Matériaux, who is examiner in this thesis. And we have Julien Clodon, who is PhD advisor of Saptarshi, who is a senior scientist at CEA Grenoble, and Jean-Michel Gérard, who is co-advisor, who is also senior scientist at CEA Grenoble, and myself, who is president and from Institut Néel here, and senior scientist as well. So, Saptarshi, you have 45 minutes about to present your work. The floor is yours.
Thank you. Oh, yes. Yeah, thank you. Thank you. Am I audible? Maybe not. Am I audible?
Yeah.
Okay. So, good afternoon, everyone. I'm Saptarshi Kotal, and I will present to you my work from my PhD project, which was carried out under the supervisions of Julien Clodon and Jean-Michel Gérard at the Nanophysics and Semiconductor Group in the CEA of Grenoble. My project aimed at developing, at controlling spectral properties of quantum light sources based on a quantum dot in a nanowire. In particular, I focused on single photon sources. Now, to have single photons on demand, we must have a source that is capable of generating precisely one photon every time it is excited. Now, this emission must be in a well-defined direction so that it may be collected by some form of collection optics. An ideal source must be efficient, which means every time it is triggered, it must result in an emission. It must be pure. The emissions must be pure. That means contains exactly one photon. And each photon emitted must be identical to every other photon emitted by the same source. Now, such sources are highly desirable for various applications across multiple fields, such as quantum metrology, where single photons can be used as efficient and consistent standards of light flux. Then we can use such sources in quantum communication. For instance, in quantum key distribution, where sensitive information may be encoded in the polarization state of a photon, thereby making it inherently unbreachable. Finally, we can also use them in quantum simulation, where photons can serve to simulate quantum systems that can be modeled in supercomputers. An example of such a problem is boson sampling. Now, the component that emits photons in our sources is the quantum dot. A quantum dot is a semiconductor nano inclusion, which is surrounded by a semiconductor of a different band gap. Now, in particular, we use indium arsenide quantum dots, as we see here, which is of the order of 10 nanometers in diameter, and it's surrounded by gallium arsenide, and the entire system is grown by molecular beam epitaxy. Now, the contrast in band gap between indium arsenide and gallium arsenide results in a strong confinement of charges within the quantum dot, thereby leading to discrete energy levels. Now, that's why quantum dots are often referred to as artificial atoms. Now, the ground state of such a system exhibits a completely filled valence band and a completely empty conduction band. Upon imparting some energy to the system, an electron may be excited from the valence band into the conduction band, and the remaining absence of the electron can be treated as a positive quasi-particle, which we call a hole. Now, attractive Coulomb interaction between the hole and the electron results to a bound state, which we call an exciton. After a certain amount of time, the two carriers may recombine, thereby emitting a photon, which in our case happens to be in the order of 950 nanometers. Now, the quantum dot must be re-excited again to be able to emit a photon of the same wavelength. Now, quantum dots in general are considered very appealing sources of single photons at cryogenic temperature because they provide a stable emission. The probability of emitting a photon with every pulse is close to 1. The lifetime of the excited carriers is rather short, which results in a very high emission rate. And finally, such quantum dots can be very easily integrated into much more complex systems. However, despite all these assets, quantum dots also present some challenges. Most of the emission of the quantum dot remains trapped within the high refractive index host material. Thus, only about 1% of the light is actually collected outside. Additionally, self-assembled quantum dots display a dispersion in emission wavelength because of their individually varying morphologies. Now, such a dispersion is a major hindrance for multi-source applications. Then the quality of the emission is further hampered because the quantum dot tends to interact with its surrounding. So there are sources of noise in the surrounding which make the line width of the emission broaden compared to the radiatively limited line width of the quantum dot. Now, the dominant sources of noise in our systems arises from either charge fluctuation in the surrounding or phonons that come from lattice vibrations. Now, when you have charge noise, the fluctuation of charges around the quantum dot results in a fluctuating electric field at the level of the quantum dot, which makes the optical transition energy of the quantum dot fluctuate, which translates into a broadening of its emission spectrum. Lattice vibrations, on the other hand, act on the quantum dot through the interaction between acoustic phonons. These phonon modes generate strain on the quantum dot, thus modifying the emission energy of the emitter through deformation potentials. Now, two main effects of such kind of a coupling can be observed. First, we notice the apparition of two phonon sidebands on either side of a spectrally thin Lorentzian line shape, which is called the zero phonon line. Particularly on the left side, we have the sideband corresponds to the emission of a photon associated with the absorption of a phonon. And on the right, we have the emission of a photon accompanied by the emission of a phonon. Now, the second effect that we observe is the actual broadening of the zero phonon line itself. This happens due to quadratic interactions between the emitter and the surrounding. And it's associated to phonon scattering of the exciton, which is excited by virtual excitation to higher excited states. I mean, such a process generally involves much higher energy phonons, and therefore we don't generally see this effect at cryogenic temperature. Photonic nanostructures are used to help in collect the light that are emitted by the quantum dots. And two main categories of structures are used. We have mainly the microcavities, as seen on the left, and the waveguides on the right. An optical cavity relies on accelerating selectively the cavity mode, the spontaneous emission into the cavity mode, thereby making it the preferential emission channel. In doing so, in accelerating the spontaneous emission, it of course makes it less sensitive to the sources of noise around the quantum dot, but at the same time, it results in a very narrow operation bandwidth. Waveguides, on the other hand, make the guided mode the preferential emission channel. And they do so by suppressing the spontaneous emission in all unguided modes. Because there is no spontaneous emission acceleration in the case of the waveguides, it results in the emission being more susceptible to the noise in the surrounding. However, we have a much broader bandwidth. In particular, we work with the waveguide approach. Now, photonic nanowires are a kind of waveguide which are very similar to optical fibers. In particular, we have a cylinder made of gallium arsenide, which has a diameter of the order of 1 wavelength in the matter. At this diameter scale, of course, the waveguide confines the guided mode strongly in the two transverse directions, making it possible to achieve a spontaneous emission rate which is very close to that of the bulk. Additionally, a dielectric screening effect significantly reduces the coupling of the emitter to free space modes. This happens due to the suppression of the 0-point fluctuation of these modes within the material. In other words, the free space modes have no means of getting into the wire itself. Therefore, the emitter has no possibility of coupling to them. And in the process, we can achieve almost an order of magnitude in inhibition of these free space modes. Now, photons emitted by a quantum dot must be collected in some way to be able to use them. So what we do is we work on the two extremities of the nanowire that I've just shown you. First, we introduce a hybrid silica gold bottom mirror, which presents a a reflectivity of around 90%. This helps to reflect the downward propagating emission. And in the process, it also results in a small acceleration of the spontaneous emission. On the other extremity, we introduce a taper in order to adiabatically expand the mode outside the nanowire in order to achieve a well-directional beam. Also, the taper at the top helps to eliminate the reflections from the top facet. Now, such nanowires are grown by, they're not grown. They are developed by a top-down etching process, and we call them needles. Similarly, they can also be developed by a bottom-up molecular beam epitaxy growth process as well. Now, another interesting geometry that we use is what we call the photonic trumpet. It functions identically to a photonic needle as seen earlier, except in this case, the guided mode is expanded within the material rather than outside it. Now, such nanowire devices have enabled the fabrication of bright and pure single photon sources. They help to funnel the spontaneous emission into a very directional beam, having a Gaussian profile. Finally, they offer a very broadband operation, which helps to simultaneously collect the emission from various detuned quantum dot transitions. Finally, this broadband nature of these nanowires has also enabled to develop a wavelength tunable single photon source recently. Now, the principle that was used to tune the quantum dot in the trumpet was to bend the trumpet. Now, as the trumpet bends, a part of the trumpet is compressed, while the other part is stretched. So this results in a stress gradient across the quantum dot plane. Now, when the quantum dot experiences this stress, which is predominantly uniaxial and directed along its growth axis, if it's compressed, it undergoes a blue shift in its band gap. And if it's stretched, then it undergoes a red shift in its band gap. Now, the wavelength tunable source was demonstrated in a modified scanning electron microscope chamber, as seen here, at 5 Kelvin temperature. The top facet of the trumpet was physically bent with a tungsten tip. And in the process, about 1 micrometer of displacement was achieved, which resulted in roughly 25 milli-electron volts of tunability. Now, although such a system was useful to show a good proof of principle, such a system used to tune the quantum dots is rather cumbersome, and therefore an integrated solution would be much more desirable. In the course of my PhD, I helped to design and fabricate such an integrated device where we introduced 2 electrodes on either side of the photonic trumpet. Then, by applying a potential difference across the 2 electrodes, we were able to displace the top facet of the trumpet. And by applying different potential differences, we could shift the emission wavelength by a maximum of 0.37 nanometers. What we see here is the graph as a function of applied voltage and the corresponding wavelength shift. Now, these measurements were carried out by Fabrice Donatini and Matteo Finanzer, and with these 0.37 nanometers of optical shift is equivalent to roughly 700 times the radiative line width of a quantum dot in these systems. Now, while nanowire antennas have enabled impressive results in the field of single photon emission, how do they fare when it comes to generating indistinguishable photons? To address this, let's look at the results that were independently carried out both in the group of Richard Warburton in Basel and the group of Jean-Philippe Poisat here in Grenoble. So the quantum dot transition was resonantly excited with a spectrally thin laser, and in so doing, resulted in the following spectrum. Now, as we can see, this spectrum exhibits a 6 microelectron volt line width. Now, mind you that a quantum dot in this system would have a radiatively limited line width of the order of 0.7 microelectron volts. That means the measured line width is almost 10 times larger. Next, to understand the cause of this broadening, a spectroscopy of noise was carried out on the quantum dot by now setting the energy of the laser slightly detuned from the quantum dot resonance. And in so doing, it made it possible to probe all the sources of noise that are responsible for making the central frequency of the quantum dot fluctuate. By doing a Fourier analysis on the resulting intensity fluctuation of such a signal, the following spectra were observed. Now, on the left, we look at the low frequency regime, so anywhere up to 1 kilohertz of frequency. We see that the noise spectrum decreases as 1 over f, which is often associated to the charge noise in the surrounding. More interestingly, on the higher frequency regime, discrete and isolated peaks were observed. Now, after doing some finite element simulations, this showed a correspondence to the first three vibration modes of the nanowire. Here, F1 represents the first fundamental flexural mode, where the trumpet oscillates from side to side. F2 and F3 are the second and third harmonic of the flexural mode. And L1 is when the trumpet extends and contracts vertically. Now, even at 4 Kelvin temperature, this experiment showed that there is enough thermal agitation in the system to be able to thermally excite these vibration modes. At this point, two strategies can be foreseen to produce indistinguishable photons in a nanowire. The first would be to understand the channels of decoherence of a quantum dot in a nanowire and to devise solutions in order to suppress them. Now, in the course of the previous experiment, we see that the vibration of the nanowire is a dominant source of noise in the system. And therefore, in the course of my PhD, I worked on developing a theoretical model in order to study the impact of all the modes that are supported by by the nanowire. And I will present to you these results in the first part of my presentation. A complementary approach would be to accelerate the spontaneous emission, thereby making it less sensitive to noise on the surrounding. And for this, I will present a new type of nanocavity in the second part of my presentation. Now, let's begin with the first approach. So the experiment presented by Munch et al. Allowed the identification of only the first few thermally excited vibration modes of the lowest frequency of the nanowire. But in reality, a much larger set of modes are responsible. A larger set of modes can, the nanowire can support an infinity of modes. And so we set out to answer the question of what extent of the observed spectral broadening was due to only the vibration modes of a nanowire. To address this question, we implement the following theoretical model. We consider a quantum dot to be a two-level system, which is coupled to the vibration modes of the nanowire, which we treat as a harmonic oscillator. Then we divide all the vibration modes into three broad groups. First, we have the flexural modes, where the nanowire flexes from side to side, generating a stress gradient across the on the cross section of the at the level of the quantum dots. Then we have the longitudinal modes, where the nanowire stretches and contracts vertically. This results in a stress which is uniform across the cross section. And finally, we have the torsional modes. These modes generate a shear stress, which on the first order do not have an impact on the band gap of the quantum of the emitter. Therefore, we just do not consider them in our subsequent calculations. The interaction between the modes and the emitter is treated by the following interaction Hamiltonian, where G0 corresponds to the coupling strength. G0 is given by two terms, one in red, which represents the shift in emission band, shift in quantum dot band gap per unit of stress applied. And the term in blue represents the amount of stress generated for a given amount of top facet displacement of the nanowire. UZPF is the 0-point fluctuation of the vibration modes. Then the photon emission spectrum S of omega can be calculated as the convolution product of the radiatively limited line shape, which is SRAD, with the individual contributions to the broadening brought by every individual vibration mode. So for a given vibration mode M, we have Sm of omega, which is given which is governed by the following parameter, which we name theta m squared. Theta m squared itself is dependent on the coupling strength, the vibration mode of the vibration mode frequency, and the phonon population in the mode. Now, two regimes can be identified as a function of theta m squared. First, we consider when theta m squared is greater than 1. In this case, we observe that the spectrum is predominantly composed of a comb of spectral lines, which has a Gaussian line shape. And in other words, in this case, the quantum dot energy somewhat adiabatically follows the motion of the nanowire. Now, this regime is generally governed by the low frequency modes. Next, we consider when theta m squared is much smaller than 1. Here we observe, we name this the perturbative regime. We observe a zero phonon line with an amplitude of almost 1, flanked by two spectrally isolated side bands having an amplitude much smaller than 1. This regime is governed by high frequency modes. I programmed a script to allow to calculate the impact of individual modes on the emitter. Therefore, from the finite element calculations that were performed, and here I represent theta m squared as a function of the mode frequency for the first few modes up to a frequency of 3 gigahertz. As we can see, the impact of each mode progressively decreases as their frequency continues to increase. Now, the complete quantum dot emission line shape can be, as I said, was calculated by combining the contributions of every individual mode. Here I represent a quantum dot, which is precisely positioned on the axis of a needle nanowire. Such a quantum dot would experience only the longitudinal modes. And we plot here in gray the radiatively limited line shape. And as you can see, by considering modes up to a frequency of 8 gigahertz, we have the blue curve. Clearly, the vibration modes have a significant effect on the line shape. Now, such a deterioration is further amplified when the quantum dot is now positioned closer to the edges of this nanowire. Now they experience not only the longitudinal modes, but also the flexural ones. And however, quite interestingly, we noticed that by suppressing the impact of the first 7 vibration modes of the lowest frequency, we are able to retrieve the radiatively limited line shape. And this is represented by the dotted black curve on both cases. So from this, we conclude that yes, the vibration modes are a major source of decoherence in quantum dot embedded in a nanowire. This source of decoherence is strongly position dependent of the emitter, and it's dominated by the contribution of a finite number of low frequency modes. Next, we look at photon indistinguishability as a figure of merit to evaluate the impact of the modes on the emission decoherence. So indistinguishability is defined as the overlap of the temporal wave functions of 2 photons, which is equivalent to the output of a Hongomandl 2-photon coalescence experiment. So here we notice that when the quantum dot is on the very axis of a nanowire, which is the best position that it can. In the best case scenario, we obtain only about 70% of indistinguishability. And even if the quantum dot is shifted by about 20 nanometers from the axis, we obtain an indistinguishability as low as 40%. And for a quantum dot positioned close to the sidewall of the nanowire, it is perpetually impossible for us to produce indistinguishable photons. Therefore, a first method of reducing decoherence in such a system would be obviously from this graph to go towards low operation temperatures. And additionally, it would also help to be able to deterministically position the emitter within the nanowire. Now, working at ultra low temperatures proves to be an expensive solution. Therefore, maybe nanomechanical engineering of the nanowire itself might be a more desirable option. For this, I present three possible systems that could be used. First, we can conceive of coating the entire nanowire with a shell, with a dielectric shell. Here we use a 500 nanometer shell of silica. By adding the shell, we increase the rigidity of the system, thereby reducing the coupling between the quantum dot and the modes of the nanowire. And as we notice from the graph in blue, the graph in magenta, which corresponds to an on-sidewall quantum dot, we notice that in the worst case scenario, we have an indistinguishability of around 95%. The second solution could be to suspend the nanowire from the top, thereby leaving the quantum dots in a free and unclamped end, thus reducing the stress that they experience from the modes. In this case, now we see in the worst case scenario that the indistinguishability goes up to 97%. And finally, a third possible solution would be to introduce a 10 nanometer thin air gap between a 200 nanometer tall nanowire section at the bottom, which contains the quantum dots, and the top taper. So the air gap is sufficiently thin to minimize the optical discontinuity, but it also helps to completely decouple the system mechanically. Now, the bottom section is sufficiently small in its dimensions to have a fundamental vibration mode of the order of gigahertz. Mind you, this is almost 3 orders of magnitude greater than the standard trumpet. In so doing, now we have, for an emitter perfectly on the axis, an indistinguishability as high as 98%, and the indistinguishability exceeds 87% for all quantum dot position across the wire. So in conclusion, we have established that yes, thermally induced mechanical vibrations is a major source of decoherence in such systems. Additionally, we have shown that to subdue the impact of these modes, it is necessary to have some form of nanomechanical engineering to be able to produce high performance integrated hybrid systems. And now let us look at the second approach, which is to accelerate the spontaneous emission. So as we have already seen, waveguides offer a broad operation bandwidth, but since they don't accelerate the spontaneous emission of the emitter, the emission is more susceptible to sources of noise in the surrounding. Microcavities, on the other hand, exploit a strong Purcell effect to accelerate the emission, but in the process, they are left with a very narrow operation bandwidth. The ideal solution would be then to combine the best of both worlds. And one possible way of doing this is to use nanocavities. Now, nanocavities present an extremely small modal volume, which allows to have a relatively a significant amount of Purcell enhancement while maintaining a moderate quality factor of the order of a few tens. In the process, we can also conserve a rather broader operation bandwidth. Now, currently in literature, there are only a few examples of such nanocavities. The example comprise the photonic crystal cavity and the bullseye cavity. And now I will present a new kind of nanocavity based on a segment of a nanowire. The proposed device consists of a cylindrical gallium arsenide nanowire segment that is sat on a silica gold hybrid bottom mirror, which has a modal reflectivity of around 0.9. The top flat facet acts as the second mirror of the cavity, thanks to the contrast of refractive index between gallium arsenide and air. And this results in a reflectivity of the order of 0.4. Next, we choose a diameter of around 0.2 micrometer, which has been shown to be a good diameter to work with in our previous samples. To obtain a good transverse confinement of the mode and a strong inhibition into the free space mode. And we decide to, sorry, I don't know why it's, yeah. And we decide to work with a cavity of the order 3, which results in a height of the cavity of the order of around 0.5 micrometers. The quantum dot is then positioned on the first antinode of the cavity mode. Now, the device performance for this was performed by our colleagues in Denmark. And here we plot the normalized spontaneous emission rate as a function of the emitter wavelength detuning with respect to the cavity mode. At resonance, we expect a maximum emission, normalized emission rate of around 6.3, and a significant acceleration is maintained over a broad bandwidth of the order of 30 nanometers. Additionally, we observe that the emission into the radiative modes is strongly suppressed across a spectral range of a much larger spectral range. We also observe that a nearly perfectly monomodal operation can be expected for a spectral range around 100 nanometers wide, with beta exceeding 0.95 Again, at resonance, we anticipate a collection efficiency of the order of 0.54 for a collection lens with a numerical aperture of 0.75. To fabricate these devices, what we do is we begin by growing with molecular beam epitaxy, which was carried out by Jan Genwist. We have the growth substrate, followed by a sacrificial aluminum gallium arsenide layer. Then the gallium arsenide that will form the nanocavity, which sandwiches a layer, a sheet of indium arsenide self-assembled quantum dots. The next step consists of depositing the hybrid silica gold mirror. Then, with a flip chip process, we glue the mirror side onto a new host substrate and get rid of the growth substrate and the sacrificial layer. During my PhD, I optimized the flip chip process, making it possible to process and develop clean and defect-free membranes repeatedly with an area which is much larger than what was being achieved in the team in the past. The following steps consist the top-down processes, which involves the electron beam lithography step, then the definition of a nickel hard mask with a lift-off process, and then we put the sample into an inductively coupled plasma chamber to etch it, and thereby defining the nanocavities. The final step is to then get rid of the residue of the nickel hard mask. During my work, I also developed a new inductively coupled plasma etching recipe. The etching process consists of three broad processes that happen simultaneously. We have the physical etching process, which is anisotropic in nature and consists of the bombardment with accelerated ions on the substrate, thereby physically etching them. The second process is the chemical etching, which is isotropic in nature and relies on the reactive ions reacting with the surface of the sample, generating volatile materials which leave the sample, thereby etching it. And the third process consists of sidewall passivation, where we see the Sorry about that. We see the emergence of a protective layer on the lateral facets of the device, which prevents from further chemical reactions. Now, in the course of over 70 process optimization tests, I was able to control the relative intensities of these three processes in order to achieve the right balance to be able to define different etching profiles. In particular, I shall present two results of etching. On the left, we see the photonic trumpet. This process relies predominantly on an chemically etching process, which allows to define these undercut angles. By the end of our optimization of the recipe, we were able to obtain a routine that allowed to etch tall samples 3 times faster than what was achieved in the team in the past. This is highly desirable for etching tall samples like these. And on the right, we have the nanocavity, which depends more on a process that relies on a strong physical etching, assisted by a stronger sidewall passivation in order to define these straight vertical sidewalls. And now I will present to you the characterization results that I performed. So our sample, which is kept in a cryostat, maintained at 4 Kelvin with liquid helium, is non-resonantly excited with a pulse laser tuned at 820 nanometers. The laser is focused on the sample with a microscope objective with a numerical aperture of 0.75. The objective is also used to collect the emission of the sample, which is spectrally dispersed with a monochromator and then recorded on a CCD. Here I show you the photoluminescence spectrum of a device which is roughly 240 nanometers in diameter. Such a device typically will contain around 5 quantum dots randomly scattered across its cross-section. And the spectrum we see features isolated and sharp peaks. These peaks correspond to the recombination of excitonic complexes within which are trapped in the quantum dot. In particular, we focus on the two bright lines, which we label QD1 and QD2, and they're separated by around 13 nanometers. Additional polarization dependent analyses show that QD1 corresponds to a neutral exciton, and QD2 corresponds to a charged exciton or a trion. To determine the source brightness, what I did was to compare the saturation intensities of QD1 and QD2 with a quantum dot that was embedded in an unprocessed gallium arsenide sample. The calculated collection efficiency of such an unprocessed sample was found to be 1.2%. And as the graph shows, we obtain almost a 20-fold increase in the saturation intensities in the nanocavity quantum dots. Additionally, despite the vastly differing wavelengths of the two quantum dots, we observe that they both saturate at roughly the same level. This is a signature of a broadband operation bandwidth of our nanocavities. Next, we detect the photoluminescence of our quantum dots, but this time we record it on an avalanche photodetector. And then we perform a time-resolved measurement by calculating the time intervals between the excitation laser pulse and the corresponding quantum dot emission on a photon counter. Such an experiment would produce a time-binned photon count spectrum as seen here. We see the trend which corresponds to an ensemble of quantum dots encapsulated in bulk. This decay curve is fitted with a bioexponential function, which corresponds to the interconversion between the dark to bright and bright to dark excitonic states. And this is quite expected for quantum dots, for neutral excitons. Next, I show the graph of the charged exciton QD2. And as we see, it represents a spontaneous emission acceleration of the order of 5 times higher than that of the bulk. Sorry, not a spontaneous emission acceleration. It represents a lifetime which is 5 times shorter than that of the bulk. So with this, we have additionally a similar measurement on QD1 also showed an elevated spontaneous emission acceleration of around 4. And this is a good sign of the strong acceleration that our nanocavities produce. Additionally, again, having 2 quantum dots which have strong acceleration in spontaneous emission located within the same device, but of differing wavelengths is a proof that we also have broadband Purcell effect in our system. I was able to repeatedly observe strong Purcell effect and high collection efficiencies on several quantum dots, which were measured across various nanocavities. Although we haven't adopted any deterministic fabrication process, the quantum dots are well coupled to the cavity mode thanks to the broadband operation. Now, in these graphs, I summarize the results obtained across 10 excitonic lines taken from nanocavities of similar dimensions. The triangles correspond to charged excitons, and the disks correspond to neutral excitons. Now, the fastest line I measured had a spontaneous emission rate of the order of 5.6, and the brightest line that I measured had a collection efficiency of the order of 0.35. Now, to conclude, we have been able to introduce and demonstrate a broadband nanocavity which exhibits broadband collection efficiency and large spontaneous emission acceleration. And the relative simplicity of such a device could make it quite appealing to emergent material systems, which are unlike gallium group 3 arsenide semiconductors, not yet as sufficient, as mature as group 3 arsenide semiconductors. Now, to go beyond what I could achieve during my PhD, we could improve the collection efficiency, which is currently limited by the divergence of the far field of our nanocavity. And as we can see already, given the current design, just by having an emitter which is strongly detuned in the positive direction, we expect to have a more directional output beam. Next, thanks to the nanoscale volume of the nanocavities they are expected to have a low sensitivity to the vibrational modes of the device. Coupled to this, the fact that they also produce increased radiative rate would make them an appealing platform to generate indistinguishable photons. Alternatively, we could consider placing the nanocavities on a structured piezoelectric actuator in order to generate anisotropic strain on the level of the quantum dots, thereby restoring the symmetry of the dot to produce entangled photon pairs. Finally, we can use nanocavities for hybrid nanomechanics as well. Now, if we look at the spectrum of a quantum dot placed on the sidewall of the nanocavity, we see that even the first flexural mode generates a broadening which is in the spectrally resolved regime. The coupling between the emitter and the mode is sufficiently strong to be able to isolate even the transition corresponding to the 2-phonon state. Therefore, by optically selectively exciting one of these states with a spectrally thin laser, we could conceive of controlling the phonon population into the mode, thereby either heating it or cooling it. With that, I thank you for your attention.
Thank you very much. So we are now going to start the session of questions. So I suggest that Isabelle Robert-Philippe starts first, and then followed by Armando.
Okay. Thank you, Maxime. Thank you, Saptarshi, for your presentation of your work. So before asking you some questions, I would like first to congratulate you for the manuscript. It was extremely well written. You introduced pedagogically all the ingredients that were required to understand your results, and you detail in a very clear manner all the different steps towards the conclusion that you have from your measurements. And I must say that I'm always impressed by this kind of PhD thesis that gathers many different expertises, which involves simulation, which involves nanofabrication, also advanced optical experiment. This is a huge work. This is a huge amount of expertise to gain during the 3 years. And we all know that probably these 3 years that you spent in the lab was very difficult. especially due to the sanitary conditions that we had. So I would like to congratulate you because you managed to have very beautiful results even in these difficult conditions. These results are, as I said, very impressive. You had to tackle very different techniques, and you managed to obtain very promising results with promising perspectives. And I appreciate that the way you presented your work during your presentation, because in fact you offered another point of view of your work compared to the manuscript, and you made a selection which I think was really pertinent. So I have many questions. I will try not to be too long, but I have many, and perhaps we could go through the different topics that you tackled during your PhD. And the first one is linked to the decoherence, which is induced by the mechanical motion of the trumpets. And perhaps we could go to slide 24, where you summarize the different geometry that you propose to circumvent this broadening due to the flexural mode of the nanostructure.
I'm sorry, I didn't quite catch
the slide 24.
Yes, thank you. Yes.
Yes, and I was a bit puzzled. Okay, I understand quite well that you can effectively perhaps gain in distinguishability when you go to a coated nano trumpet, because then it's more difficult to move it, or to these suspension arms, which also isolate the nanowire from the vibrations. But I was quite surprised on the third geometry to see that in fact you lose quite a lot in terms of indistinguishability, though in fact the dots is located in a very small nanowire. And in that case, as you mentioned, the modes, the flexural mode has shifted to very high frequency, something like 2 gigahertz. So why do you lose so much in terms of indistinguishability when you go to high temperature, relatively high temperature compared to the two other geometry? I don't really understand why you have this decrease in indistinguishability there.
I didn't quite catch the last part. Why do we lose?
No, I was wondering why. In fact, when we look to how the indistinguishability evolves with temperature, you have a bigger decrease for dots on the axis and on the side walls on the third geometry compared to the two other ones. So it seems that the third geometry is less efficient in terms of indistinguishability. Do we agree?
Yes, I mean, if the quantum dot is not positioned on the axis, yes, it's not as efficient as the other ones. That's
yes, but even if they are on axis, even on axis, it seems that the third geometry is less efficient than the second one, for instance. And I was wondering why, because in fact the dot lies in a very, very small nano cavity in that case. So I was wondering why do we lose the indistinguishability of the photons in such geometry compared to, for example, the second geometry? I think because the modes are shifted to very high frequency, that this last geometry would have been the most favorable, but this is not the case.
Yes. So there is So I think there are two things that we are trying to control here. One is just we are either trying to control, just suppress the modes from appearing. Thereby, the third solution is that we are just pushing all the mode frequencies to a higher range, thereby getting rid of the lower ones. But there's also a distinct, the parameter of how strongly the modes that do exist coupled to the emitter. So that we are playing on, for instance, in the first geometry, where the modes still exist, but the coupling strength are reduced. So the impact is reduced, but for the nanocavity, sorry, not the nanocavity, but the tiny little section at the bottom, it's true that the modes appear later on, but then they're still well coupled to the emitter. So then that results, that results in a degradation in the indistinguishability.
Okay. Okay, and just for my curiosity, if you had to fabricate, for example, this structure, how would you imagine to do it?
The third one, you mean?
Yeah, the third one.
So we could conceive of growing the planar sample just like, and by then introducing a 10 nanometer thin sacrificial layer in between. And obviously the top of the trumpets would be supported by a set of pillars, which would be much more massive.
Okay. So it would be, okay.
And then
I understand.
Sorry.
Yeah, no, I understand. So you mean that we would make just a wall structure with a thin layer of, for example, aluminum arsenide that would be sacrificial, and then we will remove it just to control the distance. This was my question, because it seems that the distance between the width of the gap has to be very well controlled, and this can be done by the epitaxy. That's true. Okay, yes. Then just for curiosity, on slide 22, yeah, we see that in fact you have depending, in fact, if we look to the line width, if the dot is experimentally, if the dot is on axis or off axis, you don't see much change because they are both broad, but for different reasons. Okay, for on axis dot, this is due to the lifetime shortening, due to this kind of local, the Fermi-Golden rule, and in fact you have an enhancement of the local density of states, whereas in the second case, this is due to the coupling to the phonon. So have you tried to check the different lifetime to corroborate that in the kind of structure that you have, to say that if you have this dispersion in lifetime, though a rather equivalent line width for all the dots? Or you didn't do the experiment?
I haven't done the experiment myself.
Yeah.
But then such a measurement of lifetime was performed in the course of the work that I presented earlier by Munch et al.
Yep.
In the group of Richard Warburton.
Yeah.
So yeah, I mean, I have not measured to see if it corresponds to this, but then what they find goes quite well with our calculated results.
Okay, so you have roughly a factor of 5 in variation in terms of lifetime, though the line width is quite almost the same for all the dots.
Yes.
Okay. Then I would like to move to the nanowire cavity. So if we could go to slide 29.
Yes.
Yes. Okay, this is something that always puzzles me a little bit. In fact, you have a kind, as you mentioned, you have a node in your system, your nanocavity, whose line width is about 30 nanometer, as you mentioned here, okay? And gamma is rather constant, whatever the detuning between the emitter and the cavity. But if we go to the beta factor, it's constant. And this puzzles me a little bit. I have difficulties in understanding how you can have a resonance in the lifetime and a constant beta. For me, this is contradictory. I would have expected to have also a resonance in the beta. I don't understand why beta is constant. Because in the case when you are on resonance, you accelerate the emission, so you have a preferential funneling inside the mode. And this is not what you see in the beta. So I have difficulty to match these two curves. How do you explain this constant beta in that case? Well, I think I missed something.
I think here the fact also, it's not that we are, so the nanocavity, because of its dimensions, also exhibits a strong dielectric screening effect. So thereby, even though the acceleration is, I mean, we have such an effect in the normalized emission rates, by virtue of the fact that there are, I mean, we are anyway throwing off any other possible modes. So, I mean, there's only the one guided mode that's left to couple to. So I would explain that the beta remains constant because only it couples to only the guided mode. Whereas yeah, the lifetime kind of varies depending on whether it's on axis or on the edge. And therefore, we have a difference in the normalized rate.
Okay, then I have another question. This is more linked to the fab. If we could go to slide 30. Next slide, I think. Yes. You mentioned that you optimize the flip-chip process to get larger samples with a larger surface, up to 1 centimeter square.
Yes.
Could you tell us a bit more about the improvements that you brought to the process and how you did it? This is not much detail in your manuscript. So I would like to know, how did you manage to increase this size? Which kind of process did you implement?
So in the past, there was what we were using in the team was epoxy-based adhesive, which was used to glue the samples. And the problem with that was it had to be cured very slowly in order to prevent from air bubbles from forming inside. And the yield was something like 50-50. So you would always end up with either you get a good sample or you don't, or you lose part of it because of a bubble that formed. And what we changed during our process was we replaced the epoxy glue with a resin, a photoresist. So we used SU8 in particular, and then this resist we could also spin coat. That way we could get a more uniform surface, which was much thinner, and the curing time also was drastically reduced compared to what was used in the past. So yeah, I mean, with that we saw that the formation of the bubbles also reduced, and it was possible to now coat uniformly much bigger samples. Therefore, we could increase our sample surfaces.
Okay. Then I have another question, because it surprised me a long time ago now when we were etching pillars with chlorine-based plasma. We had an issue when using just nickel masks because in fact it was reacting with the chlorine gases, and it was becoming so hard it was impossible to remove it afterwards. So we moved towards a 2-layer masks, so that in fact first the nickel mask was etched, and then we were stopping in a resist mask that was more easy to remove. You don't have this problem? The nickel mask doesn't react with the chlorine gases in your ICP process? Is it easy to remove the nickel mask?
Yes, from experience, we have never faced that problem. Then again, I don't know the kind of chlorine gases you use. We don't use just pure chlorine.
BCl3.
Yeah, okay.
It was the same. So
no, but,
it was Cl2 and
yeah.
BCl3. So, okay, so you don't have this problem. Okay.
No,
perhaps this is due to the way we deposit the nickel, I don't know. But it was really a difficulty that we faced. Okay, that's good, because it's easier when you have just a single layer mask.
Yes.
Okay. I have also a question related to slide 35.
Yes.
Yes, so this is this one. So if I understand well, the way you try to estimate the extraction efficiency, so what you mean by epsilon here is how many photon gets out, not how many photon you collect through the objective. That's right?
Yes.
Okay.
No, it's how much we collect into the objective.
Okay, so the numerical aperture is 0.75 then?
Yes.
Okay, so I have a question for the way you estimate the enhancement is because in fact what you mentioned is that in order to calibrate the enhancement that you get, you compare to bulk, which are to dots in bulk.
Yes.
Okay. So you repeat the experiment on single dot to bulk, and then at the same wavelength on single dot in nanocavities. That's right?
That's right, yes.
Yes, and we don't have error bars. Do you have a strong dispersion in the collection efficiency when you go to the bulk or to the nanocavities? Or is it very small, the variation in the number of counts that you get at saturation? Is it rather roughly the same, or does it vary?
You mean in the...
Just for instance, for the reference sample, if you for the ref in green, if you repeat the same experiment on, I don't know, 10 dots, you always get roughly the same integrated intensity as saturation, or there is a difference?
There has been a bit of a difference, but then here I show only one of the dots just to be illustrated. But then what I did personally was I measured the lifetimes on, the saturation intensities on several dots. And then the value that I have quoted here is the average value.
Okay, this is an average value. And this is, what is the error bar that you get?
That I can show it in this one. Yes. So that's where that's the dotted lines. I put one standard deviation.
Yeah, this is here. Okay. And this brings me to another question, because in fact, okay, when you are in bulk, it should be rather constant from what I understand. But if you go into the cavities, it will strongly depend on how the dot is positioned laterally. So, because I think that when you are on the side, the lifetime and the collection efficiency shall be smaller than when you are on axis.
Yes.
Am I right? Okay.
Yes.
Okay, so this is why you see a stronger dispersion in terms of spontaneous emission rate and saturation intensity in the cavities compared to bulk. Do you think that this dispersion is related to dot position or something else? Because, for example, on the spontaneous emission rate, we see that we have almost no error bar. It's roughly about 0.6 nanosecond for all the dots, but you have a bigger dispersion in the case of the dots in cavities. Is it due to deposition or something else?
It could also have to do with the number of measurement points that I had to make the average. So, but then predominantly, yes, the deviations I would associate to the differences in position.
Okay. And if you will come back to the epsilon value that you get, you find something, if we come back, okay. So you say that you compare, in fact, to extract the efficiency, you say, okay, I compare to the ref, and then I see how much I gain in terms of intensity saturation. So which means that the epsilon ref in black, have you measured it or have you calculated it?
This has been calculated in the past for the sample that we used.
Okay.
And yeah, so we just used the value which was, because it was the same piece of sample that was.
Okay, so in fact, in your procedure, what you did is as you measure the intensity saturation in bulk, you estimated numerically the epsilon, then you measured the intensity at saturation in cavities, and then you make the multiplication. That is? Or is it also simulation, the blue and red?
No. Those are measured values.
Okay, measured value compared to bulk. Okay.
Yes, precisely.
Okay. Now, there is something which I like very much also, but you went very fast here, so perhaps we go to your manuscript. It is what you did on the electrostatically tunable nanowire single photon sources. I really like also this work. And I would like to go to figure 4.17. So I will try to give you the pages. This is on page 127. Okay, this is the one where you show the spectrum of the dots inside the pillars.
Yes.
And you selected one dot, which is a 905 nanometer, I think. But why did you choose this one and not the other one, which are better isolated? Because here they are in the forest of peaks. So I was wondering why you choose this one and not, for example, I don't know, one around 927, which are better isolated. And this is not also the most brilliant. So you choose one which is in the forest of peak and which is not the most brilliant. So why did you choose this line?
Yes, I mean, honestly, yeah, I mean, I chose these because they both showed the the characteristics of an exciton and biexciton. So I just wanted to say that, okay, we have identified an exciton and diexciton. And honestly, these measurements were really preliminary measurements just to verify that our sample was working and the quantum dots were emitting. So there was not a whole lot of data. And they were not performed by me either. So, I mean, just to put it in the manuscript, I just said that, yeah, I mean, we have both the transitions and it seems to work, just to show that, you know, we can actually go forward and do interesting things with the sample.
Okay. What you showed us on slide 14, I think, is that you have a very strong shift.
Yes.
About 700 times the line width of the dot, which is already very impressive.
Yes.
Yet, if we translate that into, if I'm not wrong, milli-electron volt, is something about 0.2 milli-electron volt shift, and your prediction is about 1.5 milli-electron volt. Is it due to the fact that the calculations are done for a dot which is really at the edge, whereas you are not completely at the edge in that case? And is it possible to estimate the dot position laterally to check that in fact the tuning is due to the fact that you are not completely on the edge but more close to the center, to explain why your shift is smaller than the one you predict?
The reason you mentioned is exactly right. So the estimation of 1.5 milli-electron volts was done with, so that was the maximum that we could achieve with the given displacement of the top. And yeah, most likely this dot was much closer to the axis of the nanowire. Now, in terms of exactly determining what the position was, we haven't done that yet. We could consider doing it, but the technique has been already shown again in Moon et al.
Mm-hmm.
And so I can describe that if you'd like.
Oh, if you wish.
Yes, with pleasure. So what we can do is, again, by performing such a noise spectroscopy, we can we have these relative intensities of the different modes of frequency, and by comparing the relative frequency of, say, the longitudinal mode, which generates a stress which is uniform and acts like a reference, with that of the flexural modes, we can estimate the amount of stress that the quantum dot is undergoing, and then we can reversely find out where the quantum dot will be positioned across the axis, sorry, not the axis, but across the radius, to experience such a stress. And this was actually done by them, and it's mentioned in their publication as well.
Okay. I have another question, which we will move to your conclusion. In the conclusion, what you showed us, you showed the radiation pattern out of the nano cavity. And that is something that puzzled you and also puzzled me, is why, in fact, you have such a higher concentration. You have a higher focusing of the mode when you get more detuned on the right side. You mentioned that in your manuscript, you had not much indication about the reason why. Is it still the case, or do you have some direction lines you would like to explore to understand this higher focusing?
So there are a few things that we suspect might be the reason, and which is probably the good direction to think of. And that is mainly the fact that a device is quite small in terms of dimensions. So what happens is, and also we have a top facet which is highly, which diffracts light at the top facet. So what happens is we lose some light, obviously, due to some reflections on the edges. And since the nanocavity is rather short, this light that is reflected off the top could potentially reflect back from the bottom mirror and interfere with the output beam. And we imagine that the interference happens in such a way for such a detuning that it produces such a directive or such a focalized beam. So yeah, I mean, currently we have found this to be highly detuned for the size of the nanowire that for the nanocavity that we worked on. But then in the future, we can precisely be aim to exploit this effect to be able to try to push the design into a more optimized version and improve the collection efficiency of the devices.
Yeah, but if you go to such a high detuning, you won't have any more Purcell effect.
Yes, precisely. So the thing is, we know that this effect occurs. Therefore, so again, the initial modelization for the device geometry that we use was done in a one-mode model, which considers just the fundamental guided mode, and then we make it reflect over the two mirrors. It's a fabric-level model. And that gave us the dimensions that we used. But then later on, we found out that such a model is not sufficient for the dimensions we are working with, because again, we have these coupling to other modes because of the reflection on the top, which can recombine and things like that. So these results are part of a full mode model, where a multitude of modes were considered. All the radiative and non-guided modes were also included in the calculation to obtain such a result. And therefore, we imagine that since something like this happens, we could potentially, by using the right model to begin the optimization step, find a sweet spot between all the parameters that would produce both a good Purcell acceleration and a directed beam at resonance.
Okay. Then perhaps, I think this is on slide 31 that you present the other perspective.
This one's 40.
Yeah, 41, sorry. I think on the next slide where you,
yes.
No, not this one, the next after. Yes, this one. Okay, so I like that very much. This idea is really exciting. And I was wondering, in fact, if we look to the spectra that you got, in fact, if I'm not wrong, you don't see really these side peaks appearing due to the phonons. What prevented you to observe these peaks up to now, and which improvement should be done to do this experiment?
You mean we haven't observed it in our experiments right now, and what we could do to begin to observe them? Right. So currently, the reason that we might not be seeing this could also be, I mean, honestly, I don't have a good estimate of what the line shape of the emissions that we're measuring right now are. But I would assume that there are also other noise sources involved, which could be broadening our measured line width. So probably these emission peaks are already within the broadened line width, so it's hard to measure it now. But in the future, we could consider, I don't know, making, maybe putting a coat around the nanocavities as they exist now, to make them a bit more rigid. That way we push the vibration modes to a much higher frequency. Therefore, we would expect these side lines to appear at a further energy. And probably that would bring them out of the measured line width, and we could expect to look at them at that point.
Okay. Okay, thank you very much. And I will finish now. And I would like to congratulate you again for your manuscript, your results, and your presentation. So thank you, Saptarshi.
Thank you. Thank you very much for your questions and comments.
Okay, so Armando, if you want to.
Yeah, sure. First of all, I would like to congratulate for this excellent work, also in view of the difficult situation in which you had to do it. I don't envy you. Yeah, the thesis is very nice, as I brought in my report. It's very rich goes from design, processing, and spectroscopy, so everything is inside. And I also enjoyed the presentation, and I also share the opinion of Isabel that it was not the same structure as in the written part. I enjoyed it. So I had many questions. I would start with the last part. So this kind of posts which you designed and implemented. I have some questions also related to the former ones on the estimation of the performance, let's say, of this kind of new photonic cavity. The first thing is this 1.2% efficiency, which you estimate. So I want to go back there. So this is a calculation, and of course your let's say your claim depends also on this number. So the use an objective of 0.75. The first question is it a glass corrected objective or not?
Yes, it is.
It's a glass corrected. So you are confident that 0.75 is really 0.75 and you're not losing because of aberrations?
No.
Okay. Okay, because at least the numbers I have in mind are definitely lower than these. We had estimated something like 1.5%, but over the full solid angle, so it's quite high. Anyway, the other thing I didn't understand is whether exactly these measurements are done under pulsed excitation or under CW excitation.
They are all done under pulsed excitation.
Okay. And the repetition rate is such that that you excite the dot only once.
It's much longer. Yes, it's much longer.
Okay. Okay, so you don't need to consider the parcel enhancement here. That's very clear.
No.
Okay, good.
You haven't repetition.
I'm not sure if sorry.
No, I was saying the repetition rate is around every pulse comes 12 nanometers apart, nanoseconds apart.
Okay, no, that's very clear. Somehow I had missed it in the thesis. Maybe it's written there and I didn't see it, or you can check that. So this is clear. Now the other thing is on the estimation of the parcel enhancement. So what you use is a non-resonant excitation. And of course, if we look at these decays, you could have different things to be considered. So first of all, you excite non-resonantly. So you need also the carriers to decay into the quantum dot, so to reach the ground state before recombine. And essentially, you are implicitly assuming that this relaxation time is negligible. Can you comment on that? I mean, who tells you that this 0.61 is really the radiative decay and it's not maybe half comes from the relaxation time? The opposite.
So first of all, our excitation regime is quite far out from resonance, so it's much lower, around, sorry, not resonance, from the power that would saturate the dot. So we are much lower to saturation at these states. And then also experimentally, I mean, we see that the
rise.
The rise is, thank you. The rise is strongly shorter in comparison to the decay of the carriers. So, normally in these situations, we anticipate something of the order of a picosecond or a few picoseconds for the. Yes. Also, another important thing is we are exciting in the wetting layer. So the carriers are trapped by the quantum dot pretty efficiently, and that happens in the time frame of a few picoseconds, which is still an order of magnitude or two smaller than the radiative lifetime. So yeah, we don't see it in our measurements.
So you have, do you have independent measurements of the lifetime taken under some resonant conditions?
I'm not sure what you're asking me.
If you have, so essentially the argument you are giving is that you see a sharp rise, and now if you have a slow relaxation, so you're exciting in the wetting layer, and then these carriers exciting in the wetting layer need to relax inside the quantum dot and reach and populate the exciton. So you're saying essentially if this relaxation would take long, I would expect a slow rise. This is the argument?
Yes, precisely.
Okay. So not only a slow decay, but also a slow rise. Mm-hmm. And probably yes. And the other question is whether you have independent measurements, so a direct measurement of lifetime, which would mean you excite resonantly, so resonant fluorescence for this kind of quantum dots.
No, we have not done any measurement of that sort.
Mm-hmm. Would you have the possibility to do that, or how would you do it?
Yeah, it could be done. I mean, I believe it's probably even it's planned in the future, but yes, it's not going to be by me, obviously.
Maybe how would you do it?
We could excite the quantum dots resonantly.
Yeah.
And then, let's say we excite it. We do a cross polarized measurement of the luminescence.
Yeah. I have another question on this still. So you said, well, I have several questions. One is, so you see an acceleration of the decay. How can you rule out this acceleration comes, for instance, from non-radiative recombination?
So we are quite sure that we do not have any significant non-radiative radiative processes, because if, let's assume there was some radiative processes, then the radiative lifetime that we would measure would have to be much faster. And over the course of all the measurements that I've made, I would expect to find some values which would surpass the theoretically expected Purcell enhancement. And currently, I mean, out of the 10, we don't see any, but then I've measured other dots as well, which we've not put in there, and we never go beyond the expected values. So yeah, we're quite sure that there's not much.
Yeah, it makes sense. Did you try to correlate actually this lifetime and the saturation intensity? Is there any? So you have measured. Did you measure the same quantum dots? So the saturation intensity and the lifetime?
Yes, here.
Yeah.
What corresponds to, yeah, it's the same dot that we have the saturation intensity at the bottom and the rate. Sorry. Yes.
These are the same. So I would need to now to process the data in my brain. The question is whether there is any correlation between these data sets, or if they are uncorrelated.
For the moment, I mean, we generally are finding pretty much a similar trend, except for one or two dots. We see if we have a high saturation intensity, we also equivalently see a relatively good acceleration.
There is, for instance, there are 2 points, the dots 3 and 4. They have high rate, but low saturation intensity. This could be an indication, for instance, of non-radiative decay or not.
No, I mean, yes, it could, but like precisely on these dots, we could, sorry.
No, I understood that you would expect then some dot very fast and even beyond.
Yes. So in this case, we would probably associate, I mean, we think that this might be because of the dot actually spending some of its time in a charged state.
Pardon?
Therefore, it might be spending some of its time in a charged state probably, so it's not always in the neutral state, and therefore we lose some collection. I mean, we lose on the collection efficiency while still having a fast radiative recombination.
Mm-hmm. Now that you are here, I see. Maybe I didn't understand it correctly. If I look at your thesis, this figure, I think it's shown at figure 320, and then there is a figure 318 where you have calibrated the average decay rate, and there you get 0.8. inverse nanosecond. And here you have 0. If I read the scale, I would say this is 0.6. Maybe I
Yes.
don't.
Yes.
What is the difference? Or
so the measurement that we performed here, the figure 318 in my thesis.
yeah.
So first of all, to estimate the reference value in the bulk, we measured quantum dots that were embedded in a large square mesa on the nanocavity sample.
Yeah.
In order to have pretty much the same kind of dots. And since there is already a bottom mirror on the whole sample, the dots that we measure are slightly accelerated because of that one downward reflection.
Okay, I see. That is considered.
Okay. For that to get the 0.6.
Okay, thank you. Another question about the how much time do I have actually?
Another 10 minutes.
Okay.
If that's all right.
I also want to too much. So about the decay dynamics. So you say you see some bioexponential decay, and you attribute it to the to flips to the dark state. Can you explain a bit more in detail what do you expect the mechanism to be?
What do you expect? I couldn't catch the last bit. Sorry.
So you see these, for instance, for QD yes. bulk.
Yes.
In both cases, actually, here when during the presentation, I understood that QD2 is a trion, or is it also a neutral exciton?
No, it's a trion.
It's a trion. So because for the QD bulk, you say this is a neutral exciton, and probably yes. This bioexponential decay comes from dark exciton, bright exciton flip. But then, why do you see that also for QD2?
We don't see it for QD2. I mean, what you're seeing here, which looks like it might be a bioexponential decay, is because it's also convoluted with the response of the setup.
I see. So this is a convolute. So this kind of bend is you attribute it to the response function.
So this is what the response function looks like.
Okay.
And then we convolute this with an exponential to get this fit.
Okay, I see. And then if you make the deconvolution, or actually you make I read that you make the convolution and then you fit.
Yeah, we go in the reverse direction, yes.
Yeah, and then you get this trend. Okay, I understand. And from the bioexponential decay, can you get some information on the spin flip time? So you need essentially a spin flip of what? Of just of the electron, or for instance, or of a hole to get this?
So what we consider is we are taking that. We assume that first the radiative rates of the two excitonic states are the same, and we consider that the two dark states also have the same up conversion rate. So we simplify the model into a 3-level problem, and then by assuming that the down conversion and the up conversion are the same rate, we make the calculation to extract the radiative lifetime.
I see. Maybe it's not strictly related to your thesis, but do you know if this spin flip is temperature dependent? So what do you expect? Actually, what is causing this spin flip? I mean, in principle, you need some sort of coupling between dark and bright states, right?
Yes. So I mean, I think it has a temperature component to it. I mean, it must be coupling to phonons. I mean, there has been a work that was done by my previous PhD student in the team on precisely these effects of spin flip in quantum dots. And there we noticed that temperature has a role to play in these effects.
Sorry?
There we see that the temperature has a role to play in for such spin flips.
Okay. So okay, but all these measurements are done nominally at
4 Kelvin. Yes.
4 Kelvin. Because I've seen you've shown a spectrum. where is it? On slide 34, where phonon sidebands are quite evident. Is that, yes, here. So is this, let's say, is this what you expected for Kelvin? It seems, just for my eye, they seem more pronounced than what I'm used to at 4 Kelvin. Are these already coming from the motion, or? This is a photonic wire, right?
Yes, it's the nanocavities. Yes.
It's a nanocavity. Okay.
Yeah.
Yeah. Yeah.
Honestly, I haven't tried to see what with our model, we haven't tried to see what the line width would look like, but
okay.
I suppose, yes.
I'm just wondering if this is already a bit temporally. I mean, if there is a temporal, a temperature effect, and because of course now if the decay is affected by temperature, then one should pay attention, I guess, for the estimation of also the parcel enhancement.
Mm.
That's why. Let me see. Okay, this I asked. This I asked. So if I have still a 1 minute. So you mentioned this idea okay, you have in the theory part, let's say, where you envision several strategies to get rid of or to suppress to alleviate the effect of mechanical oscillations. You have envisioned the possibility of coating these photonic structures with silicon oxide. Has this been done, or do you have any?
Yes.
Yeah.
I mean,
Does it work?
This can be done by a conformal growth, for instance, by ALD, atomic layer deposition, and this has been shown in the lab with nanowires, core shell structured nanowires, which were coated with silica, I think, as well.
Okay, and does it work? Or do you have results already, or your colleagues?
Oh, we haven't. I'm not aware of.
Okay.
No, we haven't done it ourselves. No.
And another question related to this. So to investigate the noise, you or your former colleagues have used set a resonant a CW laser, I guess, on one edge of the emission, and then they looked at the resonant fluorescence, or is it? So can you explain a bit, maybe a bit more in detail? What are the highest frequencies which you can get with this technique? So where does the temporal resolution come from, and what do you expect to be the highest frequency you could access? I'm not sure if it. So it's a CW laser, right?
Yes.
Okay. Can you explain how they get the temperature, the frequency resolution?
So the frequency, you mean?
The temporal resolution, yeah.
Yeah, so that would be limited by. So you have a broadening, a radiative lifetime, which is around 0.7 microelectron volts that they measured, and that's equivalent to around 160 megahertz in terms of frequency. So it would encompass, as many. It would take as many modes that can, up to 160 megahertz range of frequency modes would be able to be detected, because they would fall into the radiative language.
I was asking something a bit more experimental. So where does the temporal resolution come from? How does this measurement come?
How they perform this?
Sorry?
You're asking me how the measurement was performed physically?
Yeah.
Oh, okay. So this was done with by doing an autocorrelation of the emission spectrum. So they had two detectors where they tuned the laser and off the resonance, and then they were measuring the emitted photons split on a beam splitter, and they were measuring the correlation time across two detectors. And then by doing a Fourier analysis of the measured Fourier transform on the measured correlation signal, they obtained the following peaks.
Okay. Thank you. I'm not sure if I'm. Maybe last question, and then I guess I run out of time. So in this string tuning experiment you have shown with the needle, you have a bit of hysteresis. Do you know where this could come from?
This could also, yeah. So the fact that this method uses a physical bending of the trumpet, there's a rearrangement of charges because of the physical contact. So it could be because of some artifact from the, yes.
Yeah. Oh, maybe just a very last one. So you have mentioned, so you want to improve the indistinguishability of light by suppressing these mechanical vibrations. What about charge noise? So is it an issue in these photonic structures, or how big is it, or do you have any quantification?
Yes, indeed, we have. So what we had done was we estimated the amount of noise. So from this experiment, the 6 microelectron volts that was measured, we tried to estimate how much of this comes from the vibrational modes. And since the result also had identified,
Pardon?
So since during this measurement, they had also identified the exact position of the quantum dot that they measured, we could go back from there and estimate what the stresses that the dot would experience. And in so doing, we obtained a broadening of around 3 microelectron volts due to the vibration modes only, which means we expect the other half to be coming from charge noise predominantly.
Okay. Thank you. I think I give the word. Thank you very much, and congratulations again.
Thank you. Thank you for your questions.
Thank you, Armando. And now I suggest that Angela Vela continues.
Thank you, Mr. President. So first, I want to join the other members of this jury in congratulating you for the quality of your manuscript, which was really clear, and it was a pleasure to read it, and also the quality of your presentation today, which reflects the high quality of your work. So before I ask you a few questions, because I don't have many, I would like to thank Julien for this kind invitation to be a member of this jury today. So I met Julien 3 years ago at a conference in Grenoble, and we discussed the results we had obtained on the tuning of the emission of color center in diamond nanoneedles. And by a contactless method we developed using DC field. And so when I read a few weeks ago the nice results you have obtained about this contactless tuning of the emission for quantum dot, I was really happy. And I imagined that maybe this nice work was inspired by our work. So this is really nice. So today I have a few questions about this part of your work. So this contactless tuning. And in particular, I would like to start about the simulation you did with Consol.
Yes.
So you simulate the electrostatic force. You calculate this electrostatic force acting on the trumpet. And in the figure 4.5 of your manuscript, there is the dependence of this electrostatic force as a function of the distance of the two electrodes.
Yes.
And this was calculated for a potential difference of 50 volts. So it was a positive. So my question is, did you calculate this electrostatic force also for a negative voltage? What is the change in the optimization you can see when you change the polarization?
At this stage, I'm not sure we had tried the negative potential, but I mean, if we did, I don't think we saw anything unusual, which is why we stuck to this the dimension that gave the maximum here.
Because if you look at the results you obtain about the tuning of the wavelet, when
Yes.
you applied a negative voltage, as you can see in this plot you have on the slide 13.
Yes.
When the voltage is positive, you have this, here is a redshift. And when it is negative, you also have a redshift, which for me is strange. It is less, it is smaller, this redshift for negative voltages, but it is still in the same direction. So why? Because if you change the polarization, you should bend the trumpet in the opposite direction, not in the same. So
Yes.
how you can explain that you always observe a red shift for this one or the blue shift for the other quantum dot?
Yes. What you're saying is completely right. I mean, to be honest, we think there might be something to do with probably an inherent doping that might have occurred during the development of the device. Or, I mean, to be honest, we have not, I mean, more detailed measurements are currently in progress. So yes, we saw these things and were surprised ourselves. But at this stage, I don't think we have any conclusive proof to say why we are seeing what we're seeing. So we expected something from simulations. The results seem to be slightly different. But yeah, we're not sure exactly what it might be due to.
Yes, but for negative voltages, you don't have results from the simulations. So maybe it would be interesting to check.
By looking at this, we are thinking that maybe there's some sort of residual negative doping on the device itself. So when we apply a negative bias, instead of attracting it, it ends up pushing it back a bit. So possibly that, I mean, to be honest, we have not gone much further than that. So yeah, I mean,
okay. So
it needs to be explored a bit more before I can say something more. Surely. So yeah, right now I don't have much more than that.
Okay, I have one other question about the displacement of the trumpet you observe by SEM images, as you show here, and this displacement was really important, more than 100 nanometers. So you said it doesn't match with the simulations, so you did. But if we look at the shift, the tuning of the wavelength, and we calculate from this shift the displacement expected from the trumpet, we obtain small, so the value I calculate is a few nanometers of the trumpet. So in this case, you are not so far from the value you calculate by your simulations. So what is the agreement you expected between the simulation you did with the console and what you observe by the measurement of the wavelength shift? So it means if you have a disagreement of a few nanometers, it is enough for you, or you want to go to?
I think within a few, well, again, talking about a few nanometers, yeah. I mean, if it's, you mean nanometers in displacement or in the optical shift?
In the optical shift, you have less, but if you go from the optical shift to the shift in the X position, as you because there is a formula in your manuscript to calculate from the optical shift the shift mechanical shift. It corresponds to a shift of 5 nanometers, something like this. And from your calculation, you expect 2 nanometers, so it is not so far.
Yes. So I think, I mean, within the order of a few nanometers would be fine.
Okay.
A reason why we might be observing, I mean, in the images of the SEM that we have seen a bigger shift than we were expecting, due to the fact that we are observing with an electron beam. So in the process, we are depositing some charges on the device, which might make it more polarized. And which is why, as you rightly pointed out, that when we turn off, I mean, the measurements of the spectral shift was done with the SEM turned off. So we were just measuring the photoluminescence and looking at the wavelengths there. So as you rightly pointed out, when we are doing the wavelength shifts, it seems to correspond more with the simulation. So yeah, it's probably an influence of the SEM.
Okay. So then I have another question about the figure 419, where you show the relative displacement, and you wrote that when the bias was of about 6 volts, the trumpet is sticking on the electrode.
Yes.
So it happens just one time. Oh, and so then how did you achieve these results of the displacement up to 10 volts if the trumpet was sticked on the electrode at 6?
To be honest, that's that's indeed what we saw, but then the graph does not correspond to that because I changed it at the last minute.
Because on my copy, I have only red points. I don't have
I know.
I have 2 times red.
On an initial version of the chapter, I had a different graph which showed the sticking. And then I forgot to change the text and just change the graph. So that's why it's not corresponding.
Okay.
But no, to answer your question, it happened with one structure that we saw that it stuck at 6. But then again, so it was just on a given structure that happened. So the 10 nanometer shift, these are not all taken from the same, necessarily from the same device. So the pictures do not correspond to the spectral graph probably. They are all from similar dimensions, but not exactly the same nanowire. So it could just be that, again, because of the influence of the SEM or some additional charges on one nanowire and not on another, we saw some differences.
Okay, so you observe for one trumpet nanowire, not for another.
Yeah, no.
Okay. So in your opinion, if you will do the mechanical engineering of your nanowire, for example, you put a cap of silica around the trumpet, will you be able to apply this tuning of the emission by this electric field or not?
Well, the system would become, first, the system would become more rigid, but which means we would need more, much stronger voltages. But it also depends on the material we use to coat the trumpet, because if it's not readily polarizable, I mean, then you do not have this effect of making it bend. If it's, it is not enough carriers to.
Right.
So pretty much. So we would have to select carefully what we would want to put if we would want to. Also, I think it would not help to to make it more stiff, if the aim is to bend the trumpets easily, then I don't see why we would want to stiffen it more by putting a coat around it. If we want to tune it, I don't think we would put a coat in that case.
Yes, but then you will have a bright emission. You will have the problem related to the vibration. So if you want to find a compromise between the vibration, the width of your peak and the tuning.
Yes, so to simultaneously have both, we could conceive of other solutions as well. For instance, we could think of the third solution that we presented, where we have the decoupled taper from the bottom. And instead of using these electrodes to bend the trumpet, we could consider applying the bottom section on a piezoelectric actuator, for instance. And then by applying an anisotropic strain on the plane, we could do the tuning in that way.
Okay, it's a good idea.
This has already been shown by Armando. So yeah, we could potentially, yes.
Okay, so just a last general question. So during your PhD, you did simulation, sample preparation, optical measurement, photoluminescence, time resolved luminescence. So I was wondering which part of your work did you prefer?
If I had to rate them, I would put nanofabrication at the top. And then, yeah, I mean, I enjoyed that the most. And then I would put the optical characterization, and well, simulations were fun, but then when you have to do multiple days of simulation in front of a computer, it's... I'd rather do things with my hands than on a screen.
Okay, but thank you very much and congratulations.
Thank you. Thank you.
Thank you, Angela. So now, Christophe.
I will say for thank you. We've been eating together. I'd like to remind you. So, thank you very much. Yeah, I also congratulate you for the quality of the manuscript. That was a very well written, very clear, very good. And in fact, yeah, the presentation was better in the sense that also has been said by Isabel and others that you put up another point of view. It was very nice, so very good, and a lot of work. So that's also been said, very wide, a lot of broad range of expertise, and so very impressive, very well. So I still, my colleagues left me some questions, so I'm very happy. First of all, I'd like to thank, by the way, Julien and Jean-Michel for inviting me. So it's great, and I'm also here, so I made it, so that's good. So where are we here? So well, maybe let's stay on this one. Okay. So I have to say, like Isabel, I'm extremely puzzled by that, the third one, because I mean, there's no mechanics here. They're not coupled. It's cut. So the only way I can see something. I'm trying to work out the model again, and I think there's something. I don't know. It looks to me that there's something missing that could explain that in the model, perhaps. Or the other solution I can see is that, in fact, what we have is 3 oscillators, and that so 2 mechanical and the fourth one that couples to the 2. Because otherwise, I don't know, it doesn't make sense to me, but unless I'm seems that, especially the sort of both of them actually, the fact that the on-axis and the on-side wall, and so much difference is a bit strange, but I don't know. But so going back to the model you use, so you use a 2-level system.
Yes.
But as you know, quantum dots are, I personally love quantum dots. They are the best dirty atoms that you can find, so they're great. And so that means that they're not a 2-level system. So there is and one of the reasons is because it's usually they are misshaped. So as you know, you have, So what, so I'm assuming you haven't looked into that to look at a quasi two-level system. But just so, would you have an idea what would change, I mean, in your model? How would that make it more difficult to see now if you take a real shape quantum dot with the fact that you don't just have a two-level system, but you have the exciton splitting, for instance? Would that, how would that, I haven't thought about it, I don't know. You haven't, you know, it's a bit tough question to ask you like this.
No, I'm not getting the orders of magnitude right now in my head, but I think it's eventually comes down to something as to the order of magnitude of the splitting of the excitons compared to the phonons that they're interacting with. And I think the phonons involved have an energy which is much higher in comparison to the splitting itself. So we can come. It's probably not the best answer.
No. I mean, no. I mean, yeah. I mean, it's, yeah, sure. I don't know. I haven't, but yeah, it's probably. I don't know what to expect, but I would expect there's some changes. And like you said, whether it's a small change or big change, that's the real question. But okay. Okay, so and so can you go back to I don't know, was it about 13 also? So so this is very nice. So here I think so for that. So I think it was Angela's question, right? So for your model, the fact that you use you said, oh, I must have done negative, but I probably didn't see anything. But that's because you took everything was probably sort of perfectly symmetrical and so on, right? So in this case, I wouldn't expect any change. Is that correct? Or
no, in fact, if we look at the graph that Angela was referring to, that was actually done to define the separation between the electrode. So we basically did a parametric sweep, moving the position of one electrode, and it was not symmetrical. So one was fixed at 300 nanometers of difference, and the other one was progressively moved further apart from that 300 nanometers. So we started at a symmetric position, and we observed a maximum force generated for a separation of 600, which is roughly double that of the first electrode.
So now I'm very confused now. So which graph are we talking about here?
This is the simulation results of on page 109, figure 4.5.
Oh, right. Well, then this is strange.
The fact that it is
then indeed I would expect. Okay, then indeed I would expect that if you go from one side to the other, you would have different. And that also, and that would be to me the answer for that when because you moved it. So saying Jean-Michel, you moved it. You made it asymmetrical precisely to see sort of more effect, right? So yeah, then definitely I would expect a change in. Okay, that's fine. Voltage. Okay. Right. So staying on this. So you're saying okay. So this is nice. We can tune and with quantum dots, these dirty atoms is nice. We can tune them, so that's good. But then, so I have a quick. I don't know. Again, I don't have the answer to that. I'm just wondering. So two questions that come to it. So assuming that you have, for the first one, I think my intuition will tell me something, but the second one, I'm not sure. So if you were to look on a single photonness of your quantum dot, so would that change anything on the on the entire structure? Would that change anything in the purity? So that's the first question. And the second question is, which is more, it's on the indistinguishability. If you want to talk about indistinguishability, would that change something on the quality of your photons to your?
So if I understand your question correctly, you're asking the fact that we're applying these potentials to tune, would that change the purity and the indistinguishability?
Basically, that's it.
Well, in theory, yes, it would, but except it would affect these only after a certain amount of potential that we've applied. Because right now we're working, so if we look at this, we have the quantum dots which are right at the base here, and the field is being applied predominantly on the top. And we have done measurements to verify the field strength to see, what the quantum dots would be experiencing. And by the time it comes down, and then, oh, sorry, I didn't mention the height, which is of the order of anything from 12 to 15 micrometers in height. So yeah, for the potentials we are applying across the two electrodes, the field is practically negligible when it comes to the quantum dots. So I don't think it should not affect drastically any of the two parameters.
Absolutely. No, I was just wondering if you would move things around there. That's what. But otherwise, yeah, directly probably, but sort of indirectly, like moving things around, but whatever things are. But probably for the single photonness, I wouldn't expect changes in distinguishability. It's always, but even then, you're probably right.
Indistinguishability is pretty bad in these systems anyway. So
yeah,
I don't think it works.
Yeah, but okay. Right. What else did I have? Oh, yeah. So just very simple question. So for the, I should know. They all do that in my laboratory, but I don't know. For the ICP, so is it 30?
Yes.
I'm just wondering, because it crossed my mind. When do you know how to stop? Is it by calibration before, or like I know a little bit. My colleagues do is they calibrate by speed etching and stuff. But still, when you stop? In this stage.
So precisely what we use here is the fact that we have a gold mirror at the base. It helps because we also follow the speed of the etching, not speed, but the progression of the etching by laser reflectance.
All right. Okay. What else do I have? I'm gonna. Ça, je fais déjà. Right. Yeah. So you have. It's not mentioned any. Not really, but so because when I see, especially the 13, so the electrostatic business. So would it be interesting for mechanical sensors? Would there be an interest? I don't know. Again, this is something I don't do mechanics much. So, but
yes, it could. There's a result that has been recently published by the group of Jean-Philippe Poza.
Okay.
Nature, and that showed. So
very good.
Basically, this kind of coupling goes both ways, right? Mm-hmm. Yeah, very good for Nature.
Not far from me,
Anyway, no. So the fact that we can tune the wavelength of the quantum dot by bending the trumpet by exciting the. It works in reverse as well, because by exciting the quantum dot, you can also generate some oscillation which you can detect. So yeah, the fact that we could use them for some sort of hybrid
exactly
detectors.
No, what I don't really know is that would that give some advantage to other sensors in terms of mechanical ranges? You see, that's what I'm saying. Maybe it's, this one can measure fast ones or slow ones, or I don't know, or large range of frequencies. That's what I'm. But
so the fundamental flexural mode is of the order for such a system is of the order of 0.5 to 1 megahertz. And yeah, we could potentially go up. I think we would be able to attain the high frequency regimes which are generally quite lacking in most sensors nowadays. So yeah, that would be a benefit.
Okay. I think I've got others, but I think you've been grilled enough for no, thank you. So again, congratulations, SAP.
Yes.
Some people said that. I heard Saptashi. Oh, very good work. Well done again. Thank you for this. Thank you.
Thank you very much.
Thank you, Christophe. So I'm gonna myself take the floor, and then
Give it to yourself.
that will be Jean-Michel or then Julien. So I really have to say the very same thing about your work than the others. I really enjoyed reading your thesis. It was easy to read because it's well written, it's well organized, and the results are quite impressive, I must say. I really enjoyed it. So congratulations. I've got a few questions left by my colleagues. Actually, let's stay here. I was wondering if you can reverse the effect. So if you excite motion of the trumpet, can you detect it using the electrodes? Does it generate an oscillation in between the electrodes so that you could then use to measure the motion as a voltage modulation? That could be super convenient.
It's definitely something interesting to look at. I would imagine if there's some sort of equilibrium state between the electrode charges and the fact that it moves fast.
Well, you would have to excite in another way, like optically the motion.
Yeah, if you excite it optically and then you have a certain amount of, say, capacitance that you're measuring across
yes.
the two.
Yes.
Yeah, I mean, in that sense.
With maybe some frequency cut off somewhere, but at least for a given frequency range, maybe you can have a good detectivity.
It could probably, it could be something that could be looked at, definitely.
Okay, cool. Yeah, the capacitance might be an issue.
No, but that's the thing. You tune the capacity.
Exactly.
You do that.
Yeah. Okay. Let's see. I've got actually. So your introduction is very well detailed. I like it. And at some point you discussed dielectric screening. And you say something that I was not sure to fully understand. You say that you have dielectric screening only in the static limits. That was page 35, if I remember. And you say, you basically say that the effects disappear. Where is the sentence? This dielectric screening, actually it's page 37, is valid under the electrostatic approximation.
Yes.
And I don't see why not for propagating light. So if you have light propagating along the waveguide, you also suffer from that or not. You do generate a polarization field that follows adiabatically.
Yes.
Okay, so it's just me not understanding clearly the sentence, or?
No, I think this relates to just the calculation presented on top. So this is valid. I mean, we could estimate the rate of gamma with such an expression only in the electrostatic approximation, but it doesn't hold when they're considering.
Okay. But the effect is still working for propagating waves.
Yes.
Okay. I want something that I think is really important, and I'm not sure I understand how it's working here. So, as for the indistinguishability, what is very important is the difference between homogeneous and inhomogeneous broadening. In your calculation, it's not completely clear if there is or if there isn't an homogeneous contribution coming from the coupling with phonons. Like the square term, does it broaden the ZPL in a way that it is homogeneous?
No.
No, it's not.
Plotting is also inhomogeneous.
So is it a fully inhomogeneous broadening that the phonon generates, or is there an homogeneous part? Because in the limit where the coupling with phonon is very large,
yes,
you're going to have some homogeneous broadening, and it
yes,
can be actually a benefit for indistinguishability.
Eventually, they are both involved. Just looking.
Because that's not something you don't discuss in these terms in the calculation. And the gamma that you put in your equation 2.26 is just the radiative gamma, right? But what it should actually be is the homogeneous broadening, including every possible sources of homogeneous broadening. What do you think?
No, this already takes into account everything that we are using, because with this we are trying to compute the degree of indistinguishability of the photons. So
right.
Gamma here is taking into account the spectral, the temporal. Yes, so it's. I think it takes into account everything.
It depends on the gamma that you put in it.
Yeah, we're not using.
It's a tricky question. I have no idea what the right answer is, but I'm just wondering.
I mean,
59.
I think we are taking a gamma which is. It doesn't take only the radiative lifetime probably.
Okay. Okay. Because actually, I have an example where I'm wondering. No, sorry, it's not the same question. Okay, so it's not clear whether, so in your opinion, the phonons only contribute to inhomogeneous broadening?
No.
No.
The effect we are focused on this work takes into account only the inhomogeneous.
Inhomogeneous, okay. So in your model, the phonons will never help in increasing the homogeneous broadening?
Yeah.
Okay. 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 About the exciton-phonon interaction again. So you discuss page 59 on the different strategies to suppress phonons. So obviously cooling down is a very good idea. What surprises me a little bit is that there should be a lower limit of temperature where you don't gain anymore, because you can always emit phonons.
Yes.
Right? And do you have any idea what this temperature is, or? Because it seems to, I'm actually surprised that you nearly reach in this indistinguishability of 1. You actually do reach indistinguishability of 1, in spite of the fact that you can still emit phonons. So there is a broadening mechanism that should be there regardless of temperature, even at T = 0. But maybe it's completely negligible. I don't know. It's so small that you can't see it here. On this scale, maybe you need a log scale to see the difference. I don't know. I was a bit surprised that it goes really exactly to 1. It's page 16.
Yes.
But anyway, from what I understand, it's taken care of by your model, right? So So maybe it's just very small and you don't see any.
Probably what you're saying, yeah, it's maybe imperceptible because, yeah.
It's really flat and really, yes. So it's so small that we just can't see it and that's it.
Yeah.
Okay. All right. Very good. Yeah, I had a question. I was wondering again on Purcell. So when you are in the Purcell regime that you reach in the waveguide, so you accelerate the spontaneous emission. Does it also decrease effectively the coupling with phonons? Or is it just that you have more emission, you have a faster emission, so it dominates? Or is it really that the coupling with phonons is effectively decreased? So the coupling rate is lowered because you stay a shorter amount of time in the system, let's say.
Predominantly, that's the reason. So I think coupling strengths don't change. But then the fact that we're emitting much faster, the time scale for the coupling to act, to act on the machine is.
So if I take the absolute height of the side peaks,
yes,
do they decrease or do they stay the same and the main peak increases?
No. So basically, what we lose from the main peak's intensity, amplitude, we create the two side peaks. So actually, if we increase the amplitude of the zero phonon,
it's going to decrease. Okay, that is clear. Okay. Okay, that's very clear. Yeah, I had maybe one last question.
Maybe one last question.
Maybe, sorry, that's maybe the third last question. So in the method where you move in the static way again, the pillar, I was wondering if you could compare the coupling strengths G, because we have measured it before, but in a way that is completely different. Here you can really measure directly how much you shift the top and by how much shift the dot. So that gives you directly a G, a coupling strength. And does it match previous values, or did you try to compare? Because you make huge motion. That's like 1 micron here. So that's enormous motion with respect to what we did before when it was just vibrating with a very small oscillation. So I was wondering if such a very large motion, you were still having some coupling strength G that compare with what we had. But yeah, you need to do the calculation. So I don't know if you have the number right away.
I don't have the number to give you right now, but okay.
You didn't compare the two.
I think it's still within it's still the same. Because the method to use to calculate the shifts are still the same. So we are still applying the same factors involved to calculate G. So yeah, we assume that it's still within the same limits.
So it's comparable, you'd say. Okay. All right. So I'm going to stop here. And thanks again. And Jean-Michel, if you want to say a few words.
Yes, thank you, Mr. President. I would like to say first that, okay, it's co-supervision, but yes, I have been strongly involved in the definition of the project, but really on the daily basis, it is Julien who has taken in charge this supervision, and all the more since I had to be out of the lab during about 1 year. So I will let Julien speak about what is the daily supervision with Saptarshi and all the good we think about that. But Saptarshi, on my side, I wanted to thank you, because when a student leaves the lab, okay, we look at the scientific results, we look at the publications, and you have good publications. And but there is also something else. There is what is new in the toolbox and what will be used afterwards by others. And I have to say here that the nanocavity that you present here was not in the initial project as we had defined it. And you have been flexible enough to trust us, to follow us all along the way, because the more we realized the impact of these vibrations on the properties of the quantum dots, we more felt that the priority for the nanowire single-photon sources was to really to focus on that and solve that problem. And in the end, we not only have the concept, but we also have a structure that works and that will be used for many new studies in the next years. And in the toolbox also, what you put in, and it is also the fruit of your hard work, it is processing steps. It is the flip chip, it is the optimized etching process and so on. And so it is really the fruit of your hard work. And I wanted to thank you for the important impact you have. Not only you have had, but also you have for the next years. And also, I want to say it has been a real pleasure for me to speak with you about your results, to speak about your results in French, because Saptarshi speaks perfect French. Okay, and I would like to also express my best wishes for your future, be it in the industry or be it first in a lab for a postdoc. But I am very happy that to know that you want to stay in Europe and like in France. Thank you very much, Saptarshi.
Thank you very much.
Okay, Saptarshi, so let's talk about daily supervision. No, I would like first to warmly thank you for all the work you did during these 3 years and for all the things that you brought to the team and all the nice results. You worked hard, always with a good mood, even if you were performing some numerical simulation with hundreds of modes and writing scripts to handle this. So yes, really, thank you. I like a lot the work you carried out, because it kind of created a bridge between 2 lines of research that were independent, at least in the team. On one side, you had, let's say, quantum light sources with nanowires, and on the other side, you had hybrid nanomechanics that we investigated mostly with Maxime, Jean-Philippe, Olivier, and other people from Neil Institute. And during your PhD, you really created that bridge between these 2 thematics, showing that even if you just think about light emission, you need to think about this vibration mode, and they can be a problem. Okay, and that led to this understanding on this new decoherence channel and to this nanocavity design. So we, as said by Jean-Michel, we are really enthusiastic about this new nanowire nanocavity, because we win on both sides with them. We have the parcel effect, broadband, and also we somehow suppress largely the impact of this nanowire fluctuation. So for sure, it's a very important building block for the future. And we are going to play with them. We have an ANR project that has begun last year, but okay, it was COVID time, so it will really begin. It has already begun, but it will ramp up in speed this year. And for sure, these nanocavities, they will be at the heart of this project. And as you mentioned also at the end of the talk, if we have a quantum dot that is off-axis enough, then we have still a coupling to the vibration mode, but because we have a very small structure, this vibration mode goes to 100 megahertz, and then we are in an interesting regime for hybrid nanomechanics. And these are also new experiments we could do in the team. So really, I think this new structure will open new horizon for the years to come. And so it has been said by Isabelle and also by a lot of people, but okay, you really did a lot of things during your PhD. So numerical simulation, clean room processing, and not just taking a recipe and apply it, but you developed from scratch the etching recipe at PTA. So it was 6 months of work and of hard work because it's not easy. And in the end, we have a process that is stable that we can use to do trumpet, to do nanocavities, and this is thanks to your work, and it works very well. And you also do some optics experiments. So really a huge panel of things. And honestly, at the beginning, I was a bit afraid that it might be too much, but in the end, you succeed to tackle all the specific challenges of this many different facets to make it work and to obtain these nice results. I would like to finish by saying that it has been really a pleasure to work with you. You were super well integrated in the team, and in particular, you formed a super efficient duo with Alberto Artioli, who was postdoc at the time, and your work basically set the foundation for a lot of future results. I would like to conclude by saying thank you again, and I wish you all the best for the future. Merci Saptarshi.
Okay, thank you. So we are gonna now gather just the jury alone.
Did we lose the jury?